Okay, so this is the fifth lecture. Um, Last one here, sadly. But we're gonna end on something really nice, which is Noether's theorem and introducing Hamiltonians and maybe also Poisson brackets. And then we're gonna make some big connection between symmetries and conservations, and also generating symmetries through certain quantities. Okay, so at the end of my last discussion on symmetry, I talked about these sort of infinitesimal symmetry transformations, and we found that the details of those transformations were given by the derivative of the transformation with respect to the parameter that determins how much you do it, but at the identity, so which is when you do the transformation by no amount. Okay? And then essentially we called this transformation itself x, which is a function of, so we could call it either a function of the phase space, so q and q dot, if we're just talking about a particular point, so a particle's at some position and it has some velocity, or if we kind of have knowledge of the trajectory, then we could just think of it as a function of the position, and then we have in mind that this position depends on the time, and we know how that dependency works out. Okay, and then we looked at essentially the component functions of this. So this will map from one position to another, but that final position has a bunch of different components in terms of the degrees of freedom of the system. And so we essentially represented that as, so if we had q prime was equal to q plus x of q, then for the particular degree of freedom, we have qi prime is equal to qi plus, oh sorry, there's a delta here, because we do it by the transformation by an amount delta. So if qi prime equals qi plus xi of q times delta. And importantly, this is not a qi because this could depend on any of the degrees of freedom that tell us what the position of the particle is. Okay? So we could also write this as delta qi equals delta times xi of q, and then correspondingly this variation in the velocity is delta times xi of q dot, because these xi's, or the x, the generator of the symmetry doesn't depend on time. Okay, only the trajectory does. Okay, so now, using this, we can start talking about Noether's theorem. So, move this back a bit. So, what's special about these transformations is that they preserve the Lagrangian of the system. And so we can ask what exactly is happening, mathematically, so that these infinitesimal transformations are preserving the Lagrangian. And so what we can look at is the induced infinitesimal change in the Lagrangian that would happen when you do this transformation. Let's say you didn't know it was a symmetry in the first place. You would do a calculation like this. So the variation of the Lagrangian, well, the Lagrangian depends on the position, the velocity, and potentially the time. And so the ways in which the Lagrangian will change will come from changing each of these. So if we do this transformation, one thing to note is that we're not changing the time, right? in these transformations. These transformations are all done at one instant. So, okay. Because the transformation is infinitesimal, and so the variations in each of these things are also infinitesimal, we can evaluate what the change in Lagrangian is essentially through the chain rule. Just looking at this with derivatives. So for each degree of freedom, the change in the Lagrangian that happens due to changing the position will be dl by dqi times delta qi. This is essentially what the derivative means. It tells you how L will change because of a change in Q. So this happens for each degree of freedom, so we have to sum over all of them. And then the Lagrangian also changes due to the change in velocity. So we have to add this term dl by dqi dot, and then times delta qi dot. And then we could also add this term dl by dt times delta t, but we know that this transformation is not changing the time. So this term just goes away. Okay? Is that all right?
And is the entire equation in the sum, or is it just the dl by dt?
Yeah, everywhere there's an I, it's being summed over. So everything is being summed over. The last part that I just erased wouldn't be summed over.
Mm-hmm.
That would have just been by itself, but it's 0, so we don't have to worry. Yeah. Okay. So the next thing that we're going to say is that instead of just transforming any trajectory, we're going to specifically look at transforming trajectories that were physical. So the ones that solve the Euler-Lagrange equations. And so what was true then of those trajectories were that dl by dqi is equal to d by dt of dl by dqi dot. But remember, we defined these as the conjugate momenta. And so this is d by dt of pi, which we just called pi dot. Okay, so this being equal to this, that's what you need to remember. And so we can use this then, substitute into here. So in the first case, we know that dl by dqi is pi dot. So this delta L is equal to pi dot times delta qi plus, now this we defined as pi. So pi times delta qi dot. And I didn't write it explicitly, but I used the fact that these delta qi dots were the time derivative of the delta qi's. Right? And I think I talked about that in the last video. And so what we have then is, I can write this out a bit differently. And I'll write out the derivatives just to make it clear. Okay. Does this look familiar or something that we can do something with?
I mean, it seems as if, I'm not sure this is what you're looking for, but you can replace delta q dot I with delta x q dot. But
what do you mean by delta x?
or not delta times xi q dot, the
Oh.
equation that you have on the left.
Yeah, we can do that. I'm not going to do that yet.
Mm-hmm.
But there's something more immediate. So we have the derivative of this times this thing,
Mm-hmm.
right? And then we had just this thing times the derivative of this.
It's not coming to me.
That's okay.
Yeah, sorry.
It's not necessarily obvious. It's more about looking for a trick.
Mm-hmm.
This rule where you have the derivative of something and then times some function plus this function times the derivative of that function is what you get when you take the derivative of their product.
Oh, yeah.
Yeah, so it's the product rule. Which I don't blame you for not seeing because you don't really know that you're supposed to look for it.
Mm-hmm.
And because you know, the sum of the derivatives is the derivative of the sum, we can switch around the order of the derivative and the summation. And so what we have is the time derivative of this quantity. Okay? So now I will substitute these things in. And so delta qi was equal to delta times xi of q. And so because they're all multiplied by delta, I can just factor that out. So what I get is delta times d by dt of the sum pi xi of q. So the dependency on q is basically saying you're transforming the system or the particle at a particular position, and you would also know that particle's velocity, and then those two bits of information tell you what the Lagrangian is. So you're doing this transformation, and now you're changing the Lagrangian. This tells you exactly how to do that. Okay? Now what's crucially important is that if we know that this transformation is a symmetry of the system, then what is the change in the Lagrangian?
It would be 0.
Exactly. So that means that this thing here is 0. Okay. Does this delta matter then?
I mean, it doesn't seem so.
No, this is just a factor, right?
Yeah.
And so if I divide by delta both sides,
Yeah.
I get that. Let me write it up here because it's important. D by dt of the sum pi xi of q equals 0. And what does it mean when the time derivative of something is 0?
It's invariant, or whatever it is constant.
Yeah, exactly. It's constant over time. It's the same, which means that this quantity is conserved throughout the evolution of the system. So we have, well, don't know how that happened. We have that this quantity is conserved. And this is Noether's theorem. So conceptually, what happened is that for a particular system, which we describe through the Lagrangian, if we can find a continuous symmetry identify what its generator is, right, essentially its derivative at the identity, then based on that alone, right, we can produce a conserved quantity of the system. So continuous symmetries produce conserved quantities, which is hugely important. I think personally this is amazing, and I also think once you learn more and more about physics, you see that this is really at the heart of all physics. Not necessarily this specific theorem like in classical mechanics, but just the general idea that continuous symmetries produce conserved quantities. Okay. So what I want to do then is look at some particular systems and then see if we can determine what continuous symmetries they have, and then from that determine what conserved quantities we get. Okay? So move this one here. Okay. Right, so yeah. One thing I didn't say, it doesn't really matter, but this quantity is conserved wherever the transformation does preserve the Lagrangian. And in most situations, that's everywhere. In some situations, it's not everywhere, but that's kind of like only when you like mathematically cook up a Lagrangian like that, and it's usually not something that happens in nature. But yeah, the fact that it's kind of positionally dependent is reflected through this, but usually it doesn't matter. Okay, so let's look at some systems. So let's look at a free particle in 3D space. So a free particle has no forces, right? So no potential energy. So this thing's just moving around. What is the Lagrangian then?
It would just be the kinetic energy of the system, which would be 1/2 x dot squared, or q dot, I guess you should say.
Yeah, so since it's moving in 3D space, the position is like a vector, right? So we could say, it's okay to use Cartesian coordinates in specific cases. We just, in like these theorems and stuff, we use q because we don't know necessarily what we're going to work with.
Yeah.
So in this case, we could call it r dot squared. And if we wanted to expand this, I can just factor this out. So I get x dot squared plus y dot squared plus z dot squared. Okay? All right, this is the Lagrangian. Can we determine some symmetries from this? Certain things that we can do to the particle in a continuous way.
It seems as if you can move it to any point in the space that you're given without changing its velocity to maintain Lagrangian in the action.
So, yeah, and it would just be like, if we imagine the transformation that we could do to every point in space, would it be different for different points in space?
No?
Okay, so we're shifting everything by a fixed amount.
Sure.
Yeah, exactly. So that specific thing is a translation, right? So the system has translational symmetry. And in particular, how many different types of translational symmetries do we have for this? So you think about breaking it down into like number of real parameters.
Sure. There would be 3 translational symmetries.
Yeah, so why 3?
Because those are the number of dimensions that you can have in given 3-dimensional space.
Exactly. Yeah. So you can think of it as 1 for x, 1 for y, and 1 for z. Just moving it along those particular directions. So 1 for each dimension. Okay, so maybe let's go through them one by one. So we can translate translate along the x direction. And so as a function of, what we're going to do is basically look at the coordinates that we describe the position of the particle. How do they each transform by certain translation? So let's say we translate by an amount a along the x-axis. So where does x go to, or what does x go to, what does y go to, what does z go to?
X would go to x plus a, y would just remain as y, and z would remain as z.
Yeah, exactly. So remember, what we're trying to do is, through the symmetry, determine what x is, particularly what these xi are, then use that to immediately get what the conserved quantity is. So to get x, we need to determine this symmetry transformation, which is essentially what we've just done. So we could think of it as, so phi sub a of x, y, z, in terms of coordinates, is x plus a, y, z. Okay? So then this x is the derivative of this phi a with respect to a, but when a is equal to 0. And for the xi, that would be just looking at each component of this. So x1, which is the x direction, would be d by dA of x plus a when a is equal to 0. So what is this? And this is going to be a bit tricky because of this. So it's not going to be tricky if you know how to do it.
Yeah. It would just be 1, right?
Yeah, exactly. So the derivative, good, you didn't mess this up. So the derivative of x plus a with respect to a is just 1 no matter what.
Mm-hmm.
It doesn't matter what a is equal to. So good, this is 1. Okay, so we could then determine what is the conserved quantity associated with translations in the x direction. So, well, I guess we could compute the other values for this. So x2, what would that be?
It would be 0.
Yeah, so this is the derivative with respect to a of this component function. Doesn't depend on a, so we get 0. And similarly, x3 is 0. So the conserved quantity is, well, I can just write out the sum explicitly. The conserved quantity is p1 x1 plus p2 x2 plus p3 x3. These two are 0 because x2 and x3 are 0. And x1 is 1. So our first quantity, conserved quantity is p1, which I guess I could write these out differently as px, py, and pz. And what is px?
That is just mx dot.
Yeah, exactly. So you could do the calculation directly, or what you're probably expected to be from AP Physics is that, if I write this Will you see it?
Yeah. You
Okay.
have up until the edge of the next board.
Okay. So this is the conserved quantity, which is just the momentum in the x direction, right? The momentum that we're used to from old Newtonian physics. So what's the point here? Well, when a system has translational symmetry in a particular direction, then what we immediately know is that the momentum in that direction is conserved. So there's this, there must be this connection then between having the translational symmetry in a particular direction and no external net forces in that direction. And immediately what comes to mind is that this translational symmetry is usually broken by having a potential energy dependent on the coordinate of that direction. So like v of x. So if you have v of x, usually, and it's not constant, that breaks the translational symmetry of the Lagrangian, which then prevents the momentum from being conserved, because p dot will be equal to minus dv by dx. Okay? But I think, just thinking about it, this is like almost magical that you get this specific kind of translational symmetry, and it tells you that your momentum will be conserved. And we could do the same thing for the other translational directions. So if we translated by y, or along y, then we would get that x2 is equal to 1, and then these are equal to 0. And so the conserved quantity would be the momentum in the y direction. And then for translating along z, the momentum in the z direction would be conserved. So because in this system, there's a translational symmetry in all the directions, all three are conserved. And so the overall momentum vector is conserved.
Maybe this is just a strange way of thinking about it, but if you translate by a squared, assuming that a is any real number, it would still yield the same answer as translating by a, but with respect to the operator, that would all of a sudden cause a whole bunch of issues.
Yeah, so the difference that it makes is that the x is different, right? The derivative at the identity is different, but the derivative at the identity, since it's just a number, it's always going to be a multiplicative constant times what this would normally be. And when you have a conserved quantity, multiplying that by a constant is still conserved. So it's not just each momentum that's conserved, it's also any constant times that's conserved.
At the identity, it doesn't seem like it would be a multiplicative constant, because the derivative with respect to a of a squared,
Oh, that's
if
0,
you
right?
substituted that in, then that would be an operator of 0.
Yeah, you're right. I think the issue is that if you translate by a squared, you don't get the inverse transformations.
Ah, okay.
And
But still, at the same time, if you
Does
could
that
do
matter?
a cubed, where you can get the inverse transformation.
yeah, that's true. Things I have an answer, but I don't know if it's right. But I believe it has something to do with this, that you need this property that when you do a transformation by an amount r, and you do a transformation by an amount s, then you get this additive thing. And that has to do with satisfying a particular differential equation, which is I want to make sure I get this right. Ooh, I don't. Yeah, so it's like d by d theta of phi theta of q is equal to. Yeah, you kind of insist that this is true, but it doesn't matter where the theta is. The difference is that you basically insist on this idea of being able to do an infinitesimal transformation and then build up any transformation through this differential equation. So if you imagine you've already done it by an amount theta, so you've done it, this transformation by an amount theta to a point, and then this equation is telling you basically how to do it again, so that you would do it by doing the identity then plus delta times x to this new point. And that this equation pretty much tells you that you have to have this additive property. And so once you have that, then you're kind of constricted in the types of transformations that you can consider.
So by translating by a cubed, x of 1 would be equal to d by dq of x plus 3a rather than a cubed in that derivative?
Maybe, yeah, but you can't consider those transformations as your symmetry because it doesn't satisfy this property. Because doing it by like a cubed and then b cubed is not going to give you b cubed plus a cubed.
Okay. That makes sense then.
Or sorry, no, that's not what I meant. No, this would be true, but that's not what I was trying to say.
But like
Yeah. Sorry.
5b cubed composed of 5a cubed is not equal to.
So the specific translations by that amount, it does work, but if we're saying the transformation, like you do a transformation by a, is a translation by a cubed, and this is a translation by b cubed, composing these would be a translation by a cubed plus b cubed, but that means that this is not equal to the transformation by a plus b, because this would be a translation by the cube of a plus b,
Okay.
which is not equal to a cubed plus b cubed.
Sure.
Okay, so I didn't use this word before, mainly because I forgot, but it's not that just that we're looking at continuous symmetries, we're looking at particular sets of transformations called flows. And flows basically tell you how to take every point in a space and then move them in a certain way over some real parameter, and they satisfy certain properties, such as like being smooth. They have this property that this is equal to this. Yeah, stuff like that. And so those are the kinds of symmetry groups that you want for Noether's theorem. Okay. I'll try to do these next two examples quickly because I want to get to more stuff. So, okay. Now let's look at what we call a two-body problem. So it's a situation where essentially we have two objects, and let's say they have some gravitational pull on each other. It doesn't really matter what the specific force is, but what matters is that it has that same sort of property of being like directed towards one another, so through gravity or through electrostatic forces or something like that. So again, in 3D space, we have these, two particles or something. They exert a force on each other. And so the Lagrangian of the system, I'll just write this one out. We have the kinetic energy of the two particles. So 1/2 m1 r1 dot squared. And the square of the vector, by the way, just means the length of it squared. Forgot to mention that. Okay, so that's the second kinetic energy. And then we subtract the potential energy. And we're going to say the potential energy depends solely on the distance between these two particles. So the distance between R1 minus R2. Okay. So something like gravity or Coulomb's law, something like that will satisfy this. So do we get a translational symmetry just from translating the first particle? Like let's call this particle 1, particle 2.
No, they would have to be translated by equal amounts in equal directions.
Yeah, exactly. They have to be translated together by the same amount. So there's still an overall translational symmetry. And there's still, well, first of all, let's say why there is a translational symmetry. So the translational symmetry, or sorry, the translations preserve the differences between vectors, right? So if we go from R1 to R1 plus some constant vector A, and R2 to R2 plus A, the differences between these two will be the same because the A's cancel. Okay. So, and translations also preserve lengths in this manner. So the Lagrangian is invariant under these translations, and there are again 3 of them because we have 1 for each dimension. Okay. So we can then do this this process. Since we're a bit short on time, I'll do it myself. But it looks very similar to what we just did, because in each case, we're just doing the same operation that we did last time, just on both particles. So I'll say x1, 2, and 3 are for the first particle, and 4, 5, and 6 are for second particle. Or maybe I'll just do it this way, like 1x, if that's okay. So this is the first particle in the x direction. Let's say we're translating along the x direction. Then this is 1, and then the other 2 are 0. And then for the second particle, we get pretty much the same thing. Right, so then what's the conserved quantity? Well, we get P1x plus, P1x times x1x is 1. Then we get P2x times x1y, but that's 0. And the next one will also be 0. So we just get that. And then we get P2x times this, which is 1. And then the rest of them will be 0. And so this is the conserved quantity we get from translations along x. And this is just the total momentum in the x direction. But we have these other translational symmetries for the y and z directions. And what they tell us is that the y component of the total momentum is conserved, and the z component of the total momentum is conserved. All right, so these are just the same things, but with y and z. So each component of the total momentum is conserved. That means, as a vector, the total momentum of the system is conserved. So having this overall translational symmetry of the system tells us that the total momentum is conserved. And we could generalize this argument for any number of particles. So general translational symmetry produces conservation of total momentum. Okay?
Yeah.
Yeah. So I think this is super cool. And then the last one I think is even better. So we could do it for this system, but I'll make it a bit simpler. We're going to consider just one particle, but it's going to have a radially dependent potential. Yeah.
And that would be a rotational symmetry, correct?
Yeah.
Alright. And would it not just be the same process except with the theta instead of a x, for instance?
Yes. Okay, so we have one particle that's being pulled in towards the center, or I guess it could be pushed out away from the center. But either way, like you said, there is a rotational symmetry. But the question is, how many rotational symmetries are there that are given by one parameter?
Oh, there would be two.
Two? Why?
There would be one in the theta direction and one in the phi direction.
So you think like how I used to think, or my initial instinct, which is that we describe, a point in spherical coordinates with two angles, theta and phi, right? But if we can rotate however we want, I don't know how well I can draw this, but originally we start with our basis vectors looking something like this, right? So x, y, z. Now we can specify through theta and phi where our z basis vector is going to go, right? So you could do some rotation and get it to look like that. But there's still something to be determined, and that's where the x and y go. So from here we used two angles, which were theta and phi. So do you use phi as this angle? Or do you use phi as the angle that goes in the plane?
I've only really ever used polar coordinates in 2 dimensions, so I haven't
Oh, okay.
defined that.
So like in spherical coordinates, do you know spherical coordinates?
Yeah.
So
It's
which,
just I haven't really used them that often.
okay. So when I learned multivariable, they told me that this angle you call phi. So that's just what I'm going to do for you. But usually physicists call this theta. But for now, I'll call it phi. And the angle in the plane, we call it theta for now. So to determine the orientation of z, we had to determine how much to kind of tilt it down from where it originally was, and then we have to rotate it around. And that's determined by theta. So we used theta and phi, or phi and theta, to figure that out. But now, we need to determine where x and y go. So now that we've determined where z is, we still have one rotational degree of freedom left to determine. And so, you could call that alpha. That was not a great alpha. So there are 3 angles that we use to specify one rotation. Okay? There's another way of doing this, which involves what are called Euler angles. That's kind of complicated, and I don't want to go into it. But people also use that. I think it's related to this, though. Okay, so there are actually 3 rotational symmetries. And another way to think about this is that you can rotate about the x-axis, you can rotate about the y-axis, and you can rotate about the z-axis. And those are all independent of each other. So right now we're going to focus on rotating about the z-axis. So rotations in the z-axis. I don't want to call it this, but I'll just do this. Rotations about z. And then what we're changing is just theta, because phi is 0, and then these 2 angles kind of coincide by determining where x and y end up. Okay. So what we need to determine is what the transformation is for x, y, and z when we rotate around the z-axis by theta. And since we're doing it about the z-axis, we can kind of just do this 2-dimensionally, right? So we're taking a point that has this x-coordinate, this y-coordinate, then we rotate it by some angle theta. Maybe let's make this solid. And now we have x prime and y prime. How do we determine what x prime and y prime are?
Sines and cosines.
Yeah, and it's not the easiest. But what you can basically do is give a name to this angle, which would be inverse tangent of y over x. So I don't know, what do you want to call it?
I'm most familiar with arctan.
But let's just put a Greek letter to it.
Oh.
Because I'm not going to write out arctan each time.
What about chi?
Chi? Okay.
Yeah.
That's fine. So this, don't really have space, but this is chi. And so we know the distance from the origin is the same, right? So let's call that, let's just call that r. And so what we have is that x prime equals r cosine of the addition of the 2 angles. Y prime is equal to r sine of theta plus chi. And then we can use their angle sum formulas to figure out what these are. So where can I write it? Well, I guess I can just write out here, right? Okay, first of all, z doesn't change, right?
Yeah.
So this then is equal to, I'm really running out of space. So we get cosine theta cosine chi, right? Or shall I write it in this order? Fortunately, the diagram will have to be sacrificed. That's just how it is. So minus r sine chi sine theta. Okay? And this one is r it doesn't really matter, right? Cosine chi sine theta plus r cosine theta, or maybe, no, I'll do it this way. R sine chi cosine theta. Okay, so, but remember, I don't have the diagram up, unfortunately, but this r cosine chi was the original x coordinate, because chi was the original angle. So this becomes x. R sine chi, similarly, was the original y. And this is x. And this is y. Okay. So when you do linear algebra, you'll learn that this is the form of the transformation when you do a rotation. But you don't know linear algebra, so I thought I should just derive it. Okay. So x goes to this, y goes to this, and z stays the same. This is an example where changing one coordinate can be determined by other coordinates. And what's the point now? Well, we want to figure out what each of these xi are. So for x1, what do we do?
What are we trying to do again?
So we figured out the transformation, right? Based on what theta is. And now we need to find x, or rather xi, right? So that's just x, but for a particular coordinate.
So that would be the derivative with respect to theta of the transformation of x. Right?
Yeah, I'll just write it out. And where do we do that?
What do you?
Like, so we differentiate it, right? And then.
Oh, at the identity.
Yeah, exactly. So we do this at theta equals 0. And what is this?
That would be negative x sine theta minus y cosine theta.
Yeah. And what is cosine theta at
that would
0?
Be 1.
Yeah.
So it would just be negative y.
And then x2.
That would be d by d theta of x sine theta plus y cosine theta. Which is,
At theta equals 0?
yeah.
Which is?
And that would just be x.
Yes. Okay, a little harder than last time, right? But we've gone where we need to get. And so we can now figure out what the conserved quantities are. So we'll do it here. Keep these up. So we have P1, right? Which again is just going to be the momentum in the x direction. But P1, let's call it Px. Then times x1, we get minus y. And then plus py times x2, which is x. So I'm going to write this as, oh wait, I just wrote the same thing. Sorry, it's py times x. So this is equal to x py minus y px. Now, I don't know if this is familiar to you. It might not be.
Yeah, I don't recognize it immediately.
So what this actually is it's the z component of r cross p. I don't know if r cross p is familiar to you.
Yeah.
What is r cross p?
That is the cross product of r and p, or the perpendicular component to both of them.
So there's a particular quantity in physics that this is.
Oh, that's the torque, isn't it? Or
It's close. So torque is r cross f, right?
yeah, so it's the derivative of torque.
Or the torque is
Or
the derivative
integral,
with
yeah.
respect to time of.
Which would just be the angular momentum.
Exactly. So this probably you need to do a little, like one more physics class, like an introductory college physics class that you see this. But r cross p is exactly the angular momentum. And so this is the z component of the angular momentum. So what we found is that, what did we talk about? The symmetries were rotations about the z-axis, and what we produced was that the z component of the angular momentum was conserved. Okay, well, we just arbitrarily chose this, right? Rotations about z. And because there's this overall rotational symmetry, it doesn't matter what axis we pick. It's just the same. And so if we did rotations about an arbitrary axis, we would see that the angular momentum in that direction is conserved. So if we did a little bit more work, we could show that the whole angular momentum vector is conserved. And that is simply because the Lagrangian has full rotational symmetry. Okay, so I don't have time to talk about everything I want to talk about, but I'll finish up on some maybe important notes. We found that let me erase some stuff.
I definitely knew r cross p was the angular momentum. It's just I was not expecting it in that context at all. So
Well, that's
it's
almost a
not
good
fun.
thing,
Yeah.
because that makes it feel more important.
I'm really kicking myself for that now.
No, it's okay. It's okay. Don't worry.
I should have done that.
You'll learn through going through college and whatever. It's just you're not going to be able to do everything or just remember everything, and that's okay. Right. So we found that translational symmetry, so translations, produce conservation of momentum, right? So there's this connection between translations and momentum. And then rotational symmetry resulted in conservation of angular momentum. I'll just write the whole thing out. Okay, so if you're like me, you think that this is wonderful and amazing. One of the most incredible, like, just concepts or theorems in physics. But if you still don't really care about this, or you think, well, this is just kind of a niche thing, who cares? Like, what does this have to do with, our old ideas of conservation of momentum and angular momentum? Well, it really has more to do with why should we have translational symmetry and rotational symmetry? And it comes from a more basic idea of what this we would call homogeneity, which I'll do with a capital H, it's pretty important. Homogeneity of the universe. And this talks about the isotropy of the universe. And so homogeneity is basically saying that if you go wherever in the universe, the laws of physics should really be different from where you started, right? You can go anywhere, the laws of physics should always be the same. And isotropy is basically saying that there's no preferred direction that the universe has. You can go and look wherever, and laws of physics should generally look the same. And this is just kind of the expectation that, nature is pretty indifferent to certain, like, coordinate choices or things like that. Those are really just human things that we put onto the universe to analyze stuff. But in general, there's just space and the stuff in it. So these are pretty reasonable things to expect. And these two things would then imply that whatever sort of formalism we use to describe nature would have translational symmetry and rotational symmetry. And then, if you use Lagrangian mechanics and you find Noether's theorem, which we did, that then immediately tells you that momentum must be conserved and angular momentum must be conserved. So those are really the big ideas that I wanted to cover and that we've gotten to now. I think it's a really nice way to finish this off. So thank you for coming all these days. I know you didn't really have to, especially with exams coming up. But yeah, I hope this was really interesting.
Yeah, thanks for coming.
All right.